Okay, so now we have the second best paper presented here. It's by John Bostanci, Jonas Haferkamp, Chinmay Nierke, and Mark Jandry about separating QMA from QCMA with a classical oracle.
Hello. Yeah, thanks for being here. I want to start this talk with a thought experiment. So let's say you and your mom are walking around beautiful Columbia campus, and she tells you she loves you, okay, as moms do. Um, I'm a computer scientist, and probably all of you guys are too, so you can, I feel like it's natural to ask, like, how would you prove that statement, okay? Maybe embarrassingly, my mom actually came up with the first quantum interactive proof for this. Here it is. It's a hug. But my contribution is that this proof can be made non-interactive if I just stop hugging her back. Um, but after this, I kind of, it's very natural to ask if it might be possible if there is some like classical proof, right? If there's some like mathematical way that my mom could prove to me that she loves me. And the focus of this talk is going to be about this question. So to get into slightly more detail, when we talk about proofs in computer science, the question that might come to mind is like P versus NP. So P relates to like the problems that we could solve using an efficient classical algorithm, and NP refers to problems that we could check if like an unbounded Merlin gave us a classical proof, and we were also running a efficient classical algorithm. So that's P versus NP. I do quantum computing, so very natural for me to just replace all the efficient classical algorithms with efficient quantum algorithms. But once you do this, you might notice that like there's no need to restrict the Merlin to be giving me a classical proof. He could also just give me like some quantum proof. So actually, Aharonov and Nave noticed this in 2002 in like a class that she was teaching. So you can define these two versions of like quantum NP. One of them where Merlin gives you a classical proof, and another one where Merlin gives you a quantum proof. And just for historical reasons, because the quantum version was discovered first, it's called QMA, and the classical proof version is called QCMA. And we can ask if these two are equal. So this is to get back to the hug example, like we know that the problem I started with is in QMA, and we're asking if it could possibly be in QCMA. Okay, why do we care about this? Well, it turns out that QMA, similar to NP, has a very rich collection of like complete problems that seem to capture like lots of computational tasks that we want to know about. So just to give three, like these are like vague descriptions of some like actual computational problems, but they kind of correspond to like things that physicists have been wanting to do for a long time, or like wanting to understand. So if QMA was equal to QCMA, so if every problem you could prove with a quantum proof could be also proven with a classical proof, then we wouldn't need to like use quantum proofs, right? Quantum proofs are, at least intuitively, like you should think they're kind of a hassle. Like we would have to build like quantum communication, and we'd have to figure out how to store them and all that. And it would also tell us something about like the nature of like proofs for these kinds of problems. Like maybe they're not as complicated as we thought. They all have some kind of like efficient classical description. On the flip side, like if we could separate QMA from QCMA, that means like there are problems out there that really don't have any classical proof, but you could prove them, you could check them with a quantum proof. And that's maybe like equally surprising. Okay, this is not some problem that I just made up. Actually, like people have been studying this since 2002 when Aharonov and Nave like pointed out that you could define QCMA. And sort of the work has been, ever since this like 2006 paper by Aronson and Kuperberg, to like find a more standard oracle separation. So Aronson and Kuperberg, they presented like what they called a quantum oracle separation. They also defined what it meant to have a quantum oracle separation. Somehow like their oracle separation was not super satisfying. So people have been hunting for like a standard oracle separation for 20 years now. So in this talk, I'm going to explain some of the ideas that went into this like first classical oracle separation between QMA and QCMA. And to do that, well, first I'll tell you about why the problem is so hard. Okay, so like before you even like start trying to separate QMA from QCMA, you might wonder like what is a tool that I have to do this, right? Like, And if you like kind of surveyed the like known results, you'd find that there actually aren't that many proof techniques that even like use quantum versus classical proofs. Like most of the time when people do these proofs, they kind of just like guess the witness and then say something about the resulting algorithm that comes from guessing the witness. But there's also a way to guess a quantum witness. So like most of these proofs rule out, like they prove most lower bounds, also lower bound QMA and QCMA, they don't really like distinguish between the two. And second of all, there's kind of like a structure versus randomness thing going on. So like quantum algorithms are really powerful. Like they can, they find crazy global correlations in like functions and stuff. So in order to get like a separation, you need to have like a like the verifier needs to use the proof in like an interesting like quantum way. They can't just like measure it. Otherwise, the thing they measured, I could just send that to the verifier. So somehow like the oracle, if you're searching for a classical oracle, has to have some kind of like global correlation, global structure, but then it's like really hard to rule out BQP algorithms. Like how do you know that just a normal quantum computer couldn't find that structure itself? So the problem kind of sits in like a funky spot. We have to like balance two competing desires. So I'm gonna tell you about a proof strategy. It's gonna be kind of related, like I'm gonna tell it through the parable of a fisherman. And we're gonna consider the following problem. So we have a fisher. He wants to know how many fish there are in the ocean. Okay, really he wants to distinguish between like lots of fish and not so many fish. And he's gonna be able to talk to God classically, or God will send him like a classical proof. Okay, so in a little more detail, the like cost model we're gonna talk about is like the fisherman can move anywhere instantly, but it costs him a day to fish. So this is like he gets oracle access to a set S where the fish are, and we like just want to know how many oracle queries he needs to make. And he also knows like a size parameter L. And he wants to output yes if there's lots of fish, more than L, and he wants to output no if there's like less than L over 2 fish. And he's promised that one of the two is the case. Okay? So let's just start thinking about how we would go about ruling out QCMA algorithms for this problem. So first step in any great proof is assume for the sake of contradiction that there really was a sailor with a classical witness, and he can solve this problem. So when he's sitting on the ocean with lots of fish, he says yep, and when he's sitting on the ocean and it has no fish, he's gonna say no. Well, he ought to catch a fish, right? If he never catches a fish, how would he possibly distinguish between the two cases? So here's what we can try to do. We can just put the fisherman in a pool. Okay, so there's no actual fish. We can like pretend that he's moving around, and anytime he fishes, we're just gonna say, oh, there's no fish there. Okay, but we're gonna let him like pretend that he's moving around. Well, if we like study him and see where he tries to fish, he'll almost certainly like catch a fish, right? So if we like look at where he's about to fish, we can find a position where there's very likely to be a fish, or in other words, there's likely to be a point in the set S that he's querying. Okay? Now, we can run the thought experiment again. So after we put him in the pool, he told us about a location x1. And well, what happens if we like had an actual fish in the big ocean at position x1? He would still have to say no for that ocean, and he would still say yes for the ocean that has like a lot of fish in it. So he has to, intuitively, he has to find a fish at another location. So, if he just went to position x1 and caught the fish, he wouldn't be able to distinguish between the yes and no instances unless he like went somewhere else and caught a second fish. So we can again simulate him in the pool. So we'll let him move around, we'll let him fish. If he fishes at x1, we'll tell him, yeah, there's a fish there. And if he fishes anywhere else, we'll say no. And if we study him and ask, where is he gonna fish except for x1, he'll almost certainly find another position, x2, where there's gonna be another fish, okay? And we can just repeat this up until L over 2 times, because he has to catch, like anytime we have fewer than L over 2 fish in the ocean, he has to say no. And when there's actually a lot of fish in the ocean, he has to say yes. So he has to keep finding like more and more fish when we keep redoing this simulation. Okay? And the point is like, the point is like actually we never have to put him in the real ocean. We can just like keep simulating him, put it, every time he tells us about a point, we put a fake fish there. We do it again and again and again. And we just have to figure out how to create this map. But actually, the map is like very small compared to the size of the ocean. So like we could just guess what the map is after doing this whole simulation. And it turns out like, the point is like this small map must tell the fisherman about like exponentially many. If you're thinking of L as like, some very, very large number, the map must tell the fisherman about like a ton of locations of fish. And we never had to fish in the real ocean, and it turns out this is just a very simple contradiction. Like, there's way too many ways to put fish in the ocean. There's way more ways to put fish in the ocean than there are like maps we have to guess. So we can get a contradiction from this statement. Okay. And just to recap, it might not have been clear where I'm using the fact that it's QCMA, like classical proof, but the point is that like we were like repeating this fisherman. So every time we like ran him, we like run him again to get a new point and so on. And if he had a quantum proof, he would kind of like drink the potion on the first round, catch a fish. But then when we asked him for a second fish, he'd be like, well, I drank my potion already, so I don't have it. So if we were trying to apply this strategy to rule out QMA algorithms, it wouldn't work, right? So this is like a proof strategy that kind of at least distinguishes between classical or clonable and quantum proofs. Okay. So getting back to the original problem, so what I just showed you is kind of like a high-level proof strategy for showing that this problem, set size verification, is not in QCMA. But separately, there's some work by I forget the authors, but separately you can use like the polynomial method to show that like this problem is not in QMA either, which is sad. So this problem is not separation between QMA and QCMA, but at least we have a proof strategy, so we can think about how to put it back into QMA. And this is a little trippy, but I'm going to stop using these like this ocean and stuff soon. So the idea is that we're going to add a second oracle. It's going to help the quantum algorithm out, and it's basically going to encode the Fourier transform of where the fishes are. Okay, so just really quickly, the spectral correlation problem is a problem about pairs of sets. So now we're going to let the fisherman or the algorithm query two sets, S and U, and the question we're going to ask is like, is there a state psi that has support on S, mostly on S, and whose Fourier transform is mostly supported on U? I think of them as like the floor and the wall, and it's like the shadow on the floor has to be on the green set, and the shadow on the wall should be on the orange set. Okay, and we're going to ask yes or no, right? It's gonna be a problemless problem. So either there will be a state or not. And this problem is now in QMA, and there's a very simple algorithm, which is you just check if the shadow on the floor is on S. You like you apply the Fourier transform, and you check if the shadow on the wall is on U, and you accept if both of those checks accept. Okay, and we can, it turns out we can apply the same idea from before, so we can like, if this problem was in QCMA, then we can like repeatedly ask the algorithm to get more and more and more points. So we end up with a sampler that only looks at the wall and outputs many, many points from the floor. Okay, that part is what I explained with this set size distinguishing problem, and the hard part is to show that this implies a contradiction. So now it's slightly different from what we had before, because the sampler will still get access to the wall, or the momentums, or like the Fourier transform of the floor. Okay, so how can we do this? I'm gonna just like very briefly tell you some ideas from this proof, because this part is by far the most involved part of the paper. But the idea is to try to understand what does querying the wall tell you about the floor. And one way that we do this in computer science is what's called lazy sampling. So if we want to understand like what you know from querying something, we can imagine like we can imagine you're querying like some algorithm who's like making up information on the fly and only remembering what you know about the state. It turns out there's an equivalent technique quantumly called the compressed oracle technique. It's kind of similar, but like it happens in superposition. I'm not going to really explain. But when you apply this technique to this spectral correlation problem, it turns out like a couple of ideas from physics pop up, and it's kind of crazy that this is how it is. But it turns out you can model this as like a collection of bosons, or like particles that like are allowed to be in the same position. And when you look at a point Y in the U oracle, it kind of just like looks like you're bouncing off pairs of these particles with equal and opposite momentum. Okay? And a lot of work goes into this, but basically we can prove that these pairs of bosons are like they're kind of like uniformly spread out throughout the position. So you can't actually guess their position as long as they're paired up. They're not always going to be paired up, because like you can like kind of double bounce them. I'm not going to get into the details, but basically you do a bunch of like this idea of like the fact that they're paired up means that they can't be found implies a contradiction. So just to quickly talk about some takeaways, but because I'm basically out of time. Some problems are only meant to be proven once. Like, I started this talk talking about quantum versus classical proofs, but really it's more about like clonable or copyable proofs. So we give evidence that there's some problems for which quantum proofs can solve better, but actually like the main point is like these problems can't be solved in a way that's like clonable or repeatable, or like in a way that you can share with your friends. Because any such proof would imply a contradiction. But sometimes this is actually a desirable thing. Sometimes this is great. So quantum money and verification at quantum computation are two examples where we actually want this to happen. Of course, these are like still super hard problems, but hopefully this work gives us some insight into how to achieve some of these real-world applications of quantum computing. Thank you.
Are there any questions? I think that's a feature of morning talks. Everyone is still falling asleep. So what can be done next with this? Once we know that they are separated, can they be actually special case of, I don't know. So now we have separation.
Yeah.
What one can do next?
Well, I mean, there's lots of like, I think like myself and Mark kind of got into this problem because we're trying to understand quantum money, which is like one of these big things in quantum cryptography. So there's lots of cases where you actually want something not to be clonable, and this kind of gives us maybe some insight into how to do that. And I think there's also a lot of other like problems in complexity theory or like oracle separations you can like hope for, like with IP or pH and QMA. Yeah, I don't know what like specifically people would want to do next, but there's like a whole world of problems that one can explore.
Okay, good. Thank you again.